Hello. Today we will continue with our last course on motion and mechanics. So far, we know what happens during a free fall. We know what happens during a projectile. We can imagine what happened during a circular motion. Our lesson today is what happens during what is called a simple harmonic motion. Example of that is a mass spring system where I put a mass and I compress the spring, then the spring will push the mass, then the spring will be elongated to a very high, very long distance so as it will push back, and then it will bounce again, and then it will push back, and it will bounce again. So this type of motion is called simple harmonic motion, and it is the subject of our new chapter. So what's happening is this. Let's start with an elongated position. I elongate the spring. Then what happens is I'm elongating it, so there is some force here, which is tension. The tension will pull the mass into the equilibrium position. But as it passes the equilibrium position, it will have lots of velocity, so it will continue to compress the spring. Then, after compressing the spring, there will be lots of tension. So again, it will expand the spring until it goes back to the equilibrium position. But here, there will be lots of velocity, so it will continue until it reaches again the elongated position. And it will go back, and it will go back, and then it will bounce back, and it will bounce back. And if there is no friction, this can go forever. New vocabulary that we will learn in this lesson. Period is the time needed for the object to complete one full cycle. Okay, so whenever they ask us to find the period of an oscillating object, it means they want us to calculate the time needed for the object to complete one full cycle. Okay, period we represent it by T, which is a magical T in seconds. Okay. Another new vocabulary is a frequency. It is the number of cycles in 1 unit of time, which is 1 over t. So if I have the period, I simply divide 1 over t and I get the frequency. If t is in seconds, f is in hertz. Okay, let's do a quick example. So this is from your let's annotate. This is from your book. So an FM radio station broadcasts an oscillating radio wave at a frequency. So I have the frequency to be equal to 100 megahertz. What is the period of the oscillation? Before we continue, we have to change megahertz to hertz. Megahertz equal 10 power 6 hertz. Okay. So megahertz is 10 power 6 hertz. So I come here and I say F is equal 100 times 10 power 6 hertz. So frequency is equal, how much is this? It is 10 power 8 hertz. Now, the formula T equal 1 over F, F equal 1 over T, or T equal 1 over F, it's the same thing. So T equal 1 over F, it's equal 1 over 10 power 8, which gives me 10 power minus 8. The unit of the period is seconds. Okay, because the frequency is in hertz, so the period is in seconds. Okay, let's do another exercise. In taking your pulse, you count 75 beats in 1 minute. Okay, 75 beats in 1 minute. What is the period of your heartbeat? So here you have to remember this thing, 75 beats in 1 minute, which is 60 seconds. Okay, the period by definition is the time taken for one cycle. So for one beat. So one beat will take how much? Okay. And here we use cross multiplication. 75x equals 60 implies x equal 60 over 75, which is 0.8 seconds. Okay, this is part A. Part B, deduce the frequency of these oscillations. So deduce, I have to use the information from part A. Frequency is equal 1 over the period. So it's equal 1 over 0.8, which is 1.25 per 1.25. Sorry. Frequency, part B. Frequency is equal 1 over period, which is 1 over 0.8, which is 1.25 hertz. This is in seconds, so this is in hertz. Let's go back to our simple, simple harmonic motion. Back to it. So now we know what's a period. It's the time needed for the object to complete one full cycle. The frequency is the number of cycles in 1 unit of time, which is 1 over t. Now a new definition, angular frequency. It is also a frequency, but with a different unit. So instead of hertz, its unit is radian per second. And how do we calculate it? It is simply 2 pi f. So you give me f, I give you omega. Okay? Now, let's look at the position of an object during simple harmonic motion. When it is elongated, it is at x equal x maximum. Then it goes to x equals 0. Then it goes to x equal minus x maximum. Then it goes back to x equals 0. Then it goes back to x equal x maximum. Then x equals 0. Then x equal minus x maximum. Then x equals 0. And it continues like this forever if we don't have friction. So the ball, let's start with x equal x maximum. The ball is at maximum position and will start moving to the left due to the tension force caused by the elongated spring. Remember that if an object is elongating a spring, there will be tension here. The tension will be moving the object in this direction. So it will be moving it until it reaches x equals 0. Here it will have high energy. So it will have high kinetic energy. Remember, here it will have maximum EPE, but here it will have high kinetic energy. So it will continue moving to the right and to the left until it compresses the spring. So it will go to minus x maximum. Then it will start moving back to the right due to tension caused by the compressed spring. And it will repeat the same motion. So what happens to the position is that the ball will oscillate between x maximum and minus x maximum, x maximum and minus x maximum. So let's add this x maximum to our list of vocabulary. So now we have the period. It's the time needed for the object to complete one full cycle. We have the frequency. It is 1 over t. The unit is hertz if the t is in seconds. Angular frequency. It is also frequency, but in a different unit. It's 2 pi f. Amplitude of oscillation. It's the maximum displacement of the object. We call it A. So x maximum equal A. Okay. Now, what happened to the speed and acceleration in simple harmonic motion? First, we looked what happened to the position. Now, what happens to the speed? When it is elongated, the ball is at rest. So V is 0. The spring is at maximum elongation. So the tension is maximum. So A is maximum. Here you have to remember that F equal M times A. Then the ball is in the middle. The ball is moving at maximum speed. So in the middle at equilibrium, which is x equals 0, V equal V maximum. So here 1x equal 0. Okay, here 1, x equal x maximum. Okay, here when x equals 0, the ball is moving with a maximum speed, so v equal v maximum. The spring is at equilibrium, so there is no tension, so A equals 0. No tension, no A, because tension is ma. Okay, now the ball go to the compressed stage, so x here equal minus x maximum. At this position, the object is at rest, but the spring is at maximum compression. So again, the tension is maximum, A is maximum, and A is equal A maximum. Okay, depending on the choice of the positive direction, this can be V maximum or minus V maximum. This can be A maximum or minus A maximum, but here we are taking it in absolute value. And then the same story will repeat itself. So back to equilibrium, V will be V maximum, X will be 0, A will be 0. At elongated position, X will be X maximum, V will be 0, A will be A maximum. Equilibrium position, X equals 0, V equal V maximum, A equals 0. Compressed position, X equal minus X maximum, V equals 0, A equal A maximum. Okay, so we find out that when x equal x maximum plus or minus we have A equal A maximum. Okay, but when x equal 0, we have velocity equal V maximum and A equal to 0. Okay, here we have velocity equal to 0 and A equal to A maximum. Oh, now, two formulas you need to memorize, which is V maximum equal omega, which is 2 pi f, times A, which is the amplitude. A maximum equal omega squared times A. Okay, so these are the omega and the A that are in the list of vocabulary. Okay. Let's solve another exercise. Sorry. On windy days, the top of a building oscillates with amplitude 40 centimeters. So we have the amplitude is equal 40 centimeters. We always change to meters. So this is 0.4 meters. And the period of T equal 7.7 seconds. Seconds, I don't change the units. What are the maximum speed and the maximum acceleration? So here I have to remember that V maximum is equal to omega A. Okay, A maximum is equal omega square A. Okay, what is omega? Omega is 2 times pi times F times A, which is the amplitude. This will give me 2 times pi times F square times amplitude. Okay, now what is F? Let's do the F on the other side. F is equal 1 over T, which is equal 1 over 7.7, which is how much? 1 over 7.7, 0.13 hertz. So now I come here. This is equal 2 times pi, which is a 3.14, times F, which is 0.13, times the amplitude, which is 0.4. And this is equal 2 times 3.14 times 0.13 times 0.4. This is equal 0.326. The unit for speed is meter per second. And now for A maximum, I'll do the same. This is equal omega to 2 times 3.14 times F, which is 0.13, all of it square, right? Times amplitude, which is 0.4, and this will give me 0.266 meter per second square. Okay, you find the solution here with all the needed formulas in order to solve the problem. We can model the motion of a bee's wing as simple harmonic motion. A bee beats its wings 250 times per second. Okay. So 250 times in 1 second. Okay. And the wind tip moves at a maximum speed of 2.5 meter per second. So I have the maximum equal 2.5 meter per second. Now, what is this 250 times per second? This is actually the frequency. Okay, remember the frequency is 1 over time. Okay, that is 1 over seconds. So it is in hertz. It's 1 over time. So this frequency is 250 hertz. And I have the V maximum. What is the amplitude of the wingtips motion? So I will use V maximum is equal to times omega times amplitude, which is 2 times pi times F times amplitude, which is equal so V maximum is 2.5, right? This is equal 2 times pi, which is 3.14, times the frequency, which is 250, times the amplitude. So I get the amplitude is equal to 2.5 divided by 2 times 3.14. 2.5 divided by 2 times 3.14 times 200. So A is equal to, we get the answer 1.59 times 10 power minus 3 meter. Okay. Last exercise, an air track glider attached to a spring oscillates within an amplitude of 25 centimeter. So we have here the amplitude is equal 25 centimeter, which is 0.25 meter. The glider completes 10 oscillations in 33 seconds. So 10 oscillations in 33 seconds. Okay, calculate part A. The period, I have to remember that the period is the time for one oscillation, right? So I say 10 oscillations take 33 seconds. One oscillation takes how much? So I get 10 times x equal 33. Implies x equal 33 over 10, which is 3.3 seconds. Okay, part B, the frequency. Frequency is equal 1 over t, which is equal 1 over 3.3, and this is equal 0.303 hertz. Part C, the angular frequency. omega. This is equal 2 pi f, which is equal to 2 times 3.14 times f 0.303 implies omega equal 1.9 radian per second. So remember the units. Part D, what is the maximum speed? So we memorize this. The maximum is omega times A, which is equal 1.9 times the amplitude, which is 0.25, and this is equal 0.475 meter per second. Okay, so that's it for today's lecture. See you tomorrow with new concepts. Bye-bye.